We present Height Recon, a new approach for efficient 3D scene reconstruction. Given posed colour images as input, our goal is to accurately reconstruct the 3D shape of the observed scene. Several approaches exist that produce a 3D model that explains the observed parts of the scene, and a subset of these methods are also capable of estimating the shape for the unobserved regions. However, many of these existing methods employ large and expensive to compute models, making it infeasible to deploy them in real-time online settings. Our new proposed Height Recon method attempts to address each of these requirements. We achieve this by relaxing the expectation for full 3D reconstruction and instead aim to predict a similarly accurate 2.5D height field as shown on the right. Here we show an example online reconstruction from our method running in real time on a 1080 Ti GPU. We will now explain the main components of our Height Recon method. First, a 2D network is used to output a depth map and a set of deep features for each image in the currently observed input sequence. Next, we aim to generate an initial noisy estimate of the height field. To do so, we integrate the depth maps into a TSDF using the known pose of each image and raycast this volume from above, locating the heights at which the values change from positive to negative. Unlike many existing learning-based methods that store dense feature volumes, our TSDF only records a float 16 and a uint8 per voxel, making them very efficient. Given our raw estimate of the height field, we now aggregate the per-image features into a top-down feature map by projecting the 3D points into each camera and bilinearly sampling, using the predicted depth maps to account for visibility. The final stage in our pipeline involves refining the initial raw height field using a top-down 2D network. As these operations are performed in 2D, this refinement is much more efficient than the equivalent 3D feature volume refinement. This step also allows our model to make predictions for regions in the scene that are only partially observed in the input images. We find that simply regressing a refined height field leads to overly smooth results, whereby the depth details observed in the input are lost. To address this, we introduce a learned blending step that combines the output of the refinement network and the raw height field. This produces the final complete height field, which is denoised while also retaining detail. Here, we present comparisons to two recent full 3D learning-based reconstruction methods. On the left, we show the input images for a test scene in the ScanNet dataset. On the right, we show first-person online reconstructions for each method. Notice how the expensive full 3D learning-based methods, NeuroRecon and Atlas, lag behind the real-time camera motion as they require additional time to process each frame. In contrast, our method is efficient, thus opening the door to time-sensitive augmented reality or robotics applications. As an example, virtual characters can interact with a new scene, but only to the extent to which it's been reconstructed. The user, holding a handheld device, is gradually moving and looking around and avoiding obstacles. From a third-person view, it's clear that our height fields-based method, Height Recon, allows virtual characters to go further sooner. Additionally, here we show a demo of an occlusion-aware augmented reality application enabled by our method. Finally, we show our Height Recon model running on two sequences, captured using a handheld mobile device, where camera poses are estimated using visual inertial odometry. On the left, we can see the online reconstructions rendered back into the current camera view, and on the right, we show the final reconstructions. Notice that even with poses estimated using only visual inertial odometry, our model is able to produce sensible reconstructions with coherent geometry, demonstrating that Height Recon can be used for mobile phone-based real-time AR applications. Thank you for watching. Please see the paper for more details.